infinity and back again. I'm to them. Young dog and I talking. You know once in the shine, don't vex when you get married. Me nah make trouble stress my brain. Cut checks me, I cut to the chase. Start never second hand, never second in command. Never stopping for a second, talking up on the line. Look a jump and sound, I go try and make
Joining us for the first time, welcome. The goal of our community is to provide a platform for knowledge sharing on all things Kotlin. We get together every few months for meetups like this one, and we really hope you enjoy it. A big thank you to Zopa for hosting us this evening at their amazing office. So thanks to David and the rest of the team for putting up with us. In terms of the lineup for this evening, we have 3 talks for you across various different topics. Be around sort of 20 to 30 minute mark each. After the second talk, we'll have a break, which is when the pizza is going to arrive. And at the end of the evening, we will be heading to the pub. It's going to be the Horniman, which is in Hayes Galleria. The address is on the meetup page, but if you just follow the crowd afterwards, I'm sure you'll be fine. And now I'd just like to hand you over to Ash for a very, very quick introduction to Zopa.
Cheers, Ben. Hey, everybody. Welcome. Really excited to see so many of you here for another Kotlin meetup. I'll just go through some logistics first of all, just in case you don't know where the bathrooms are. If you haven't been here before, just follow the wall on the left. It's over there. And if the fire alarm goes off, it is a real fire alarm. We'll have to talk about GC functional Kotlin downstairs in the courtyard if that happens, but hopefully not. If I can tell you a little bit about Zopa, we are a retail bank that have been around for quite a few years, started off as a peer-to-peer lender before that. We're heavily invested in Kotlin engineering, particularly on the server side. And yeah, in terms, if I can give you some numbers, I guess, to do with Zopa, probably 700 people altogether working for Zopa. 230 of those are in the technical functions, so very much fintech. And right now we have about 40 vacancies in technology. So if you want to know more about Zopa, what we care about in terms of technology and the sort of things that we get up to, please just feel free to approach anyone who's got one of these badges on. We'd love to hear from you. I shall leave it at that. I think it's probably best if we get on with this show. To begin with, I think we're going to have Noah and Luke. Do you have slides that introduce you, or shall I introduce you?
What we do actually.
Yeah. Okay, I'll just pass it straight over.
Oh. Hello. Hey, so we're here today to talk to you about functional domain modeling in Kotlin. I'm Noah. I'm a software developer here at Zopa, and I've been here for 2 years, and I work in the car finance department.
I'm Luke, and I used to work at Zopa in the same team as Noah.
But still representing with the shirt. Good effort. So what are we going to cover today? So we're going to present a very simple domain, and we're going to show how you can model this in an object-oriented programming way. And we're going to talk about some functional programming concepts to show how it can make your code easier to manage and less error-prone. And these are concepts which we've used at Zopa and we found really helpful. So if you're sitting there feeling like this cat, don't worry, we're not going to go over what a monad is or any lambda calculus or anything. Our aim from this talk is just to show you that these functional programming concepts are really useful and you can start using them in your own code today. So let's present the domain. Let's imagine we're going to provide a platform for providing loans to customers. We're working with a domain expert to understand what the requirements of this platform are. One of the requirements is that customers need to be able to make a payment on their loan to reduce their outstanding balance. So from this, we can learn 3 really important concepts about our domain. We can learn the payment, loan, and outstanding balance. And domain-driven design teaches us that having a ubiquitous language is really important for keeping everyone on the same page when discussing the domain. We've definitely had problems in the past where different terms have meant different things to different people, and we've ended up in a big mess. So let's see how we could do this in an object-oriented programming way. We might have something like this. So we've got a loan class with 2 properties or fields, the ID field, which is a unique identifier representing the ID of the loan. And we've also got the outstanding balance, for which we use a big decimal, and we use the var keyword. So we use var here because the outstanding balance is going to change throughout the life cycle of the loan. So in object-oriented programming, it's common to keep the behavior with data. So we can add the apply payment function inside the loan class. So here it just accepts a payment of a big decimal, applies some very basic validation, and then reduces the outstanding balance by the payment. And it does this via mutating the state. But what do we not like about this? So yeah, with mutable state, so Joshua Block in effective Java says that classes should be immutable unless there's a very good reason to keep them mutable. And this is because they don't work well in multi-threaded environments, and it kind of becomes harder to reason about the state of entities when the state can mutate. So Kotlin actually comes with built-in support for making classes immutable. So we can change the outstanding balance field to use the val keyword, and therefore it becomes an immutable class. And what does this mean for the behavior? So now with the behavior, we have to return a copy of the original loan with the outstanding balance changed. So instead of mutating it, we're now just returning a copy. And we get the copy function for free because we're using a data class for the loan. And in functional programming, it's common to keep data and behavior separated. So for example, we might have a separate module for the payment behaviors, and we can extend the loan class with the apply payment function. So let's take this to production and see how it goes. So a few hours later, we get a call from our support team. A customer has made a payment, but somehow their outstanding balance has actually increased. So we get on our computers, we debug through everything, and it looks like there's a bug in the system. It looks like the loan class has been instantiated with the incorrect outstanding balance. And because we've been using the outstanding balance as a big decimal, it's really easy for developers to pass in the wrong kind of data here. And it looks like that's what's happened here. So what can we use to improve this? We can use algebraic data types. And that's kind of just a scary word for a type made up of other types. I like to think of these as sort of like, imagine a shopping basket is a type, and it's made up of other types of your groceries, like your milk, your cheese, your tomato. So a certain kind of algebraic data type is the product type, where there's an and relationship between the types. So here we can say that the loan is made up of a loan ID and an outstanding balance. We can model this in Kotlin using value classes. And these are special type of classes in Kotlin, which can only have one field or one property. They're kind of like wrapper classes. And so here we have the loan ID class, which wraps a UUID, and we have the outstanding balance class, which wraps a big decimal. And the special thing about the value classes is that at runtime, the underlying value is represented instead of the wrapped type. So you don't get any performance impacts by using them. So now we can model the loan class as an algebraic data type by using the new loan ID types and the outstanding balance type. But we take this to production, and yet again, there's another issue. A customer has a negative outstanding balance showing on their loan. So we get our computers out again, and we find that even though we've used the outstanding balance type, we haven't actually defined what constraints this can have. So it's possible to have an outstanding balance with a negative amount. So let's see how we can find out the invariants of the system and how we can enforce them. So invariants are the conditions of the system which must remain true no matter what. And when we talk to our domain expert, we understand that customers can only have a positive outstanding balance, and the outstanding balance can be no greater than the maximum loan size we offer of £60,000. So we can enforce these, for example, in our value classes by using the init block, and this will run once at object creation, and we can use the require function to enforce these invariants. And the require function will throw an exception if the condition is not met. So if the outstanding balance is created with a value which is less than 0, it will throw an illegal argument exception. And this is great because now our behavior becomes much easier to deal with. We don't have to worry about the trivial validation, and instead we can just focus on the core business logic. So let's take this to production. But again, we have another issue. Customers are getting errors when they're attempting to make payments. What's going on? So with all those illegal argument exceptions getting thrown, the requests are erroring out and the customers are not able to make payments. So I'm going to pass over to Luke, and he's going to talk about what we can do.
Okay, so I'm going to talk about how we can handle these errors in a more functional way. So what Noah just described is something which I'm sure many of us are familiar with. A small error in part of our system spreads to the entire system, causing the entire system to fail. In 2014, a study showed that 92% of catastrophic failures were caused by an incorrect handling of errors. Therefore, it's crucial that we can understand how our systems can fail so we can prevent these failures from propagating to other areas of our system. So modeling domain errors explicitly can help us reason more about how our system can fail one way of doing this is that we can kind of ask the compiler to error if we don't handle every error case. And also we can use our type system to model how the domain can be invalid or can become invalid. So one way of modeling these domain errors explicitly is by using a union type. So a union type is also a type, it's also like an out-of-base data type, and it is an OR type which can be of one type or another type. So this is modeled in Kotlin using a sealed hierarchy. So in this case, we're using the outstanding balance result. So a sealed hierarchy is a special type of hierarchy where all the direct subtypes are known at compile time. So in this case, we have a failed to create outstanding balance or a successfully created outstanding balance. So going back to our outstanding balance value class, when it fails the validation, instead of throwing an exception, we return a fail type. And if it passes the validation, we return a success type. Also notice how we're using a private constructor here with a factory creator method. So this allows us to return the sealed type instead of the kind of raw value class. So let's use this let's use what we just defined in our apply payment function. So again, we need to define a sealed hierarchy for this function. In this case, a payment result. Then when we fail to create an outstanding balance, we return a fail to apply payment. And if we successfully create an outstanding balance, we return a successfully apply payment. Notice here how we're also using the when operator. So this is exhaustive. So if we don't handle every case, our compiler will error. So it's clear here how we've managed to model our errors more explicitly, and we can also use the when operator to make sure the compiler will error when we don't handle every possible error case. So there are some drawbacks with the sealed hierarchy. So imagine if for a payment, we also need to check if the loan is active. We need to update the outstanding balance, and we also need to update the date of last payment. It's very easy to end up with these kind of deep nested structures, which is not very easy to read. You also need to define a sealed interface or sealed hierarchy for every function which can error. So one thing we did at Zopa is we introduced the arrow library. So they introduced the either type, or they have the either type, which is a more generic version of the union type, which we saw earlier. And this means that we no longer need to specify a sealed type for each function. So here, the failed to create outstanding balance and outstanding balance are type parameters to this either type. And also notice here how we're using the left and right terms. So generally, left means failure and right means success. So Arrow also provides functions with working with the either type in a more imperative way. It helps us work with the either type without the kind of excessive nesting we saw earlier. So let's go back to our apply payment function. So again, we need to check the loan is active. We need to update the outstanding balance, and we also need to update the date of last payment. So here we are assigning the outstanding balance to the result of the update outstanding balance function. But notice here how the update outstanding balance function returns an either. So you wouldn't ordinarily be able to assign the outstanding balance to the result of this function. However, because we are in the either block, and because we are using the bind function, this allows us to work with the success case without having to worry about the error cases. This is because the compiler knows that if we have a success value, we must be in the success side. Essentially, if it does fail, we exit out, we short circuit and exit out of the either immediately. Essentially, we are casting to the right-hand side. So let's kind of give a comparison of the old kind of nested when way and the new more imperative way. So the new way is clearly more concise, and I hope you'll agree it's a little bit more readable as well. So what we've just seen is kind of when we encounter an error, we short circuit and we immediately return the error. Sometimes you may want to continue processing for a bit and accumulate some of these errors. For example, within domain validation. So domain validation is essentially when you have some unvalidated domain from some outside source and you wish to validate it and convert it into kind of your valid version of your domain model. So for example, if we obtain some loan DTO from some outside source, for example, some API, and we wish to kind of convert this into a validated version of that type, we can use the arrow function zipper accumulate. So the parameters of this function are independent validation blocks, which need to return the either type. And if they are both successfully validated, we return alone. If any of the validations fail, we accumulate all the errors together and return this as a list on the left-hand side. So this is kind of an image version of what I was just talking about. So here we have the outstanding balance and payment date as inputs to this zipper accumulate function. And as you can see, they're both successfully validated, so we return alone. However, for example, if payment date is not validated successfully, we return a list, in this case, just the one failure. And if both payment date and outstanding balance are not validated successfully, we return a list of failures, both of them in this list this time. So putting it all together, let's say we have some payment DTO or loan DTO from some outside source, and we use our factory creator methods to validate this and possibly accumulate errors if any of them occur. And then we apply the validated payment to our validated loan. If any of these fail, or we bind on all of these functions, and if any of them fail, we return them as a payment error on the left-hand side.
Perfect. So we after all these changes, we take this to production and we have no more issues. All our customers are happy. They can make payments on their loans. No more waking up in the morning for the support team waking us up. And yeah, everyone is happy. So yeah, just to cover what we've talked about today. So we talked about using immutable data structures and how that can help with if you're in concurrent environments, or just to help about reason about your entities a bit better. How algebraic data types can help you avoid programming issues and write easier to manage code. And how you can handle errors gracefully and get the help of the compiler to help manage error states for you. Are there any questions? That's it. Yep. From where, sorry? I don't actually know that library. I guess we can maybe talk about the result that comes in with the Kotlin library. I don't know if they're similar, but okay. Yeah, I don't know too much about that one, but yeah. But I guess the benefit compared to like the result type that comes with Kotlin is that with Kotlin, the kind of failure scenario has to be a throwable, whereas here you can have your you can write your own domain errors that don't have to be throwables, and therefore you can have sealed hierarchies within your errors, and you can handle all error cases, and the compiler can help you with that as well. Any more questions? Oh, yep. Oh, yeah, sure. So so there we were using sealed interfaces, whereas I guess we could have used a sealed class, which is a very good question. I'm not really sure, to be honest. Just personal preference, and just, I guess, yeah, I'm not really sure. Cool. Any more? Perfect. Thank you very much, everyone.
Yes. There's a spare microphone. What, turn it off? Ah, okay. I'll do that next time. Sorry for the delay. We were just waiting for Rob to get his beer. Yeah, this is Rob Moffat, technical architect at Finos, who's going to be telling us a little bit more about Finos and hopefully some stuff about Kotlin multi-platform. Over to you, Rob.
Thanks, Ben. I'll just wait for someone to change the display. Well, anyway, look, I'll just make a start. So, yeah, my name is Rob Moffat. I work as the technical architect at Finos, and Finos is the FinTech Open Source Software Foundation. And we're part of the Linux Foundation, which I hope everyone will have heard of, probably. Yes, so my job at Finos is, as a technical architect, I've got a couple of different projects that I work on. One of them is the FDC3 project, which is all about desktop interoperability. And the idea of that is to try and, if you're working in a bank, for example, if you're a trader, you might have like a big set of screens. You maybe have 20, 30 applications running on those screens. The idea of desktop interoperability is that they can all share context between them, each other. And so that's the FDC3 project. And the other project, which I think is kind of more relevant to you guys, is open source readiness, which is a project at Finos, which is all about, I forgot to do the screen share, didn't I? Brilliant. So I forgot to screen share. It's all my fault. So the other project I run at Finos is open source readiness, which is all about trying to get our members in different financial institutions to get involved in more open source software. And we run various different projects with all the different sort of member banks to try and get them to collaborate, to write code together, to meet up together, like sort of a bit like this. And yes, and then this year I'm trying to do courses and certifications around open source to try and allow developers to demonstrate that they know what they're doing and that they should be trusted. I'm sure that at Zopa Bank you do plenty of open source and you're always committing bug fixes back to the Kotlin project and stuff like this. But a lot of these sort of more old-fashioned banks, this is not really such a thing. So they worry heavily about letting developers do anything, let alone committing code to open source projects. So yeah, we're on slide like 3 now, but this is the Finos sort of member roster. So we've got probably loads of companies here that you've heard of. These are the people we're trying to sort of target with our projects and get them involved in our projects. Zopa is absent from this list. I'm sure we can sort that out after the meeting. We have a discussion about getting you guys to be members of Finos as well. But yeah, we're growing quite fast, and let's go on to the next slide. So today I'm not going to talk too much about Finos. I'm going to try and bring this all together in some kind of way. But I wanted to talk about some of my personal projects. So I don't really do Kotlin coding at Finos. I do bits and pieces of Java, Python, TypeScript, all sorts of stuff. But I wanted to tell you about a couple of personal projects because one of those I do heavily use Kotlin on. So in 2018, I wrote a website, which you can see here, which is what we called Risk First, which is all about looking at whether we could use the language of risk management for software development. So applying risk management techniques like we do in banks to the idea of software development. And this was quite popular at the time when I wrote it. And one of the ways I tried to sort of get this idea across is to draw lots of diagrams about what I was talking about. So in this example diagram here, what we've got on the left is like regression risk. So when you write some code, there's a chance that you're going to fat finger something or change something in a way that's going to affect something else in the system. It's like, well, that risk that you have there, how do you prevent that from happening? How could you stop that from happening? And if we're all good developers, we probably write lots of unit tests, and we probably have like a suite of acceptance tests and manual tests. And maybe we write a specification and we test with a specification. So if you want to get rid of your regression risk, then you've got to do those things in the middle. But out the back of that, you end up with some new risks. So maybe you end up with using lots more time on your project, or maybe you end up with this huge test suite to maintain. So your complexity is increased, or your schedule is now worse. So this was the kind of idea of risk first. And I drew hundreds of these little diagrams to sort of demonstrate what I was talking about. And I had another project that I wrote to try and to do this. And so because there were so many of them, what I did is I wrote like this simple sort of diagramming language in XML here. And I translated that into SVG. Is everyone happy with SVG? You're all familiar? Good, okay. So I translated it into SVG, and then I wrote a layout sort of engine that take all those different bits of the diagram and put them, arrange them nicely, called Kite9, and then display that as a final finished thing. We are getting to the Kotlin bit, trust me. Okay, so that was kind of my pipeline for generating these diagrams for risk first. Sorry, let's just go back at it. So after doing the risk first thing, I thought it'd be nice to actually have an editor for these diagrams. It kind of sucks that I have to write some XML all the time. And maybe this is a thing that I could, put on the internet for other people to use. So then I thought about, well, maybe I could create a web version of this. And this was all written in Java, this sort of this Kite9 translation. But I realized that, having it in Java, there's a lot of work for Java to do there on the server side. And it'd be much nicer if somebody threw a really difficult diagram at it. It'd be much nicer if it was their processor that was doing all the work and not mine, right? So I'm not going to run up some kind of massive AWS bill just processing some terrible diagrams that other people are coming up with. So I thought this is a great use case for Kotlin multi-platform. If you can run the diagram generation on the server side or on the client side, that'd be a huge win. So I started converting the Kite9 thing into Kotlin using convert Java file to Kotlin, right? Which is, you've probably all seen this, right? And I mean, there's other ways you can go with this. There's WebAssembly, and there's like various VMs that will run in the browser now. So you can actually use like TVM or something to try and run it in the browser. But I thought this was a quite a nice way to go. And I kind of felt like I really wanted to get involved in Kotlin. It seemed like a really solid choice, whereas a lot of these other things like WebAssembly just seems a bit bleeding edge. So I did this, and actually it worked really rather well. Like I was surprised, like normally converting from one programming language into another is a complete disaster. And, just nothing works. But JetBrains did a cracking job on this, and there was just very little stuff to tidy up. So this is kind of how Kotlin multi-platform works. You've basically got this sort of common platform here, and then you've got like client stuff on the right and then server stuff on the left. And the libraries you have in each slightly different. We'll come back to why that's a problem later. But on my server side, I was using this tool called Batik, which is like a really old Java library for doing SVG rendering. And on the web side, well, really the only rendering that I needed to think about was actually just how big things were in the browser. So I could use this get bbox function, which is pretty much baked into Chrome and Safari and everything else. So essentially, I did the standard programmer thing where you just abstract out the interface for the thing you're going to do common everywhere, and then wrote 2 implementations of those tiny little bits of it. And then everything else was just standard common multi-platform Kotlin. Everyone happy so far? Okay, so let's have a quick demo. I'm going to sit down now. So this is going to be interesting. I'm going to talk and operate a computer at the same time. So first of all, I'm going to show. Oh, have we lost the screen? Who's Alexander? Was that me? I've broken it, Ben. It's gone again.
Support. Jason.
Hold on, let me. No, I'm still
Help.
sharing. Stop sharing and start. Right. Okay. Let's try. Oh crikey! What's happening now? Oh, there it is. It's up, right? Okay. Right. So first of all, this is Safari, and this is the same diagram in Safari, right? And Safari is using. It's basically just taking the changes that I do in the diagram and sending them back to Java running on my machine. Java's changing it and sending it back as SVG. So it's using the original old school version of Kite9. So if I delete this element testing, say, you can see the diagram sort of slightly changes, and I can remove this one and it updates again. To make the point that it was all about sizing and stuff, if I had a bunch more text here, then it's basically working out the size of that text and changing the diagram, and I can put links in and stuff as well if I just do this. Okay, so it kind of adjusts the diagram to try and lay it out simply. It's just to make one more change. So you get the idea, right? But this is all running on the server side. So if I go to Chrome now, here's Chrome. So this is actually running on the client side. This is all going to run inside Chrome. You're kind of going to have to trust me on this, but it is actually happening. I'll show you the Chrome developer console in a second. But I can do the same things on here. So if I pull this over here, or if I don't know, pull that over there, you can see Chrome's updating. Let me show you the developer console so I can prove I'm not lying. So you can see sort of in here a whole bunch of stuff about calculating distance and stuff. So it's definitely all happening there. Right, so that's the tech demo. So next, I'm just going to dive into some Kotlin multi-platform, some details of the implementation, right? So this is my Kite9 project. And we saw, so the server Java is like Spring Boot, that's running on the server. And then this visualization is running on both platforms, right? So if I go into, so this is the layout of a multi-platform project. You've got like a common folder, and then you've got specific to the JavaScript. And then you've got stuff specific to JVM. So this is running on the server side. And then you've got JVM tests. So that whole thing I was talking about, I'm not going to try and dive into the code now. I'm having trouble reading the screen. But basically, yeah, you can see how you sort of separate out the different pieces of the code. So the common stuff is that stuff that's common to both things. Now, if I go into the build Gradle, you can see I'm pulling in the multi-platform plugin here, and then I'm telling Kotlin here to do its thing. We've got the JVM dependencies here with all the Batik stuff, JavaScript stuff happening here, and obviously it's not using dependencies here because it's all just using that get bbox function. So it's working 2 different ways. And that's kind of all there is to setting up multi-platform Kotlin. But there are a whole bunch of like gotchas that you need to think about. So I'm going to just tell you about a few of those. Let's see if this will work. Right. So first of all, the JavaScript compilation is pretty slow I don't know, probably some of you have experience of compiling Kotlin with JavaScript. It's not super good. It takes a while, especially if you make big changes. And the second thing that IntelliJ IDEA gets a bit confused with stuff. So like things out of the DOM, like element and node, these are part of the DOM model. Obviously, they are shared on both the JavaScript side and the Java side, but because Kotlin multi-platform was written without any kind of idea of a browser involved, it's like throws out warnings in IDEA, but actually in reality it just gets on with it and compiles it all. But it's kind of a mess to look at. Yeah, and I spent a long time on Gradle setup. This Kotlin multi-platform is pretty new, and so the Stack Overflow is not a super good resource for debugging problems with this. ChatGPT surprisingly was very useful in helping me with my Kotlin multi-platform problems. Way more useful than Stack Overflow in this case. And then the other thing is that you have to carry around this big Kotlin dependency to get Kotlin to run in the browser. So 2.7 megabytes is not, it's not nothing. They are trying to work on like breaking down Kotlin into like a bunch of different ES6 modules, which would be great because then you can just pull in the bits you need. So probably I'm using a tiny fraction of this whole runtime, but yeah, I have to pull in the whole thing. And because of the sort of round tripping times and everything else, I actually run a lot of stuff still in Eclipse. So I'm kind of caught between two different editors here. Yeah, and maybe that's just because I need to pay some money to JetBrains. I don't know. Yeah, last little thing is, yeah, the stack traces and the debugging when you go into the browser are not great. So this is kind of an example stack trace. Now you should be able to set source maps for all this stuff, but I've found that it does kind of work sometimes, but it's patchy. And so, when you're debugging TypeScript in the browser, that seems to be, there's like a one-to-one correspondence between what you're doing in TypeScript and what you're doing in the JavaScript that results from it. But in Kotlin, that's not necessarily the case. One Kotlin instruction could be whole reams of stuff happening in JavaScript. And then the last thing I wanted to just talk about quickly and try and bring the whole thing together was Sherlocking. Obviously, this is something that the Kotlin community maybe worries about. So the idea that, and the Java community actually talk about this quite a lot too, because Java loves the fact that Kotlin will go bleeding edge and try out a new feature. And then if it works really well, Java comes along and goes, oh yeah, we'll have a bit of that, we'll steal that. And so this has happened multiple times over Kotlin's lifetime. And I think something like Kotlin multi-platform is actually an escape from this. Kotlin multi-platform goes somewhere that Java can't go and will never go. Java's on the JVM only, whereas Kotlin is everywhere. And finally, I was kind of wondering at the end of all this, I've talked a bit about open source and the stuff I do at Finos and my own open source projects here. And I wonder, so Kotlin is an open source project, and I wonder, does making Kotlin open source, does that give you some kind of protection against Sherlocking? That code is out in the open. People want to use it, they can use it. The original idea of Sherlocking was, people like producing apps in the Mac App Store and then Apple coming along and stealing their lunch by building that into the operating system. And the original use case was an app called, I think, Watson. And then Apple came along with a search tool called Sherlock, which was basically the same thing. But we're talking about something here where none of this costs any money. It's all free. So that's my question to you guys. Is Kotlin Sherlock proof because of its open source credentials? That's the end of my talk. Are there any questions?
Thanks, Rob. Any questions? Do you mind repeating?
Yeah. Yes, that's right. IR compiler. Which Kotlin JavaScript compiler did I use? IR, yes. Which is the newer one. Yeah. You're asking if I looked at Kotlin to WASM. So I did spend a little bit of time thinking about WebAssembly, but I kind of figured this might be a bit more mature because Kotlin's JavaScript compiler had been around a lot longer. But maybe that would work. Actually, the performance seems to be kind of equivalent between the JavaScript and the JVM versions. So I'm not super upset about that, but you might be right. Maybe it would work faster. That's a really good question. I haven't benchmarked it. I'm just happy that it works. That was extremely difficult to write. Yeah, so the layout engine, I'll just touch on it very briefly, but there was somebody's PhD paper, which I kind of ripped off and then extended a few years ago. And basically, it kind of is based on some original work, but I re-implemented the whole thing in originally Java. And then as new features came along, I just kept adding new bits and pieces to it.
Any other questions?
I have looked at Mermaid, yeah. So what I'm trying to do though is slightly different, I think, in terms of the style of diagrams. So this is kind of orthogonal box and line diagrams, whereas I think Mermaid is various different things, right? It's swim lanes and yeah. I do like Mermaid as well. It's a good tool.
Any others? Good. Well, hopefully the pizza is arriving soon. But in the meantime, grab. It is. Yeah. Cool. In the meantime, grab a drink and we'll have a short break. Thanks again, Rob.
infinity and back again. On to them. Young dog and I talking. You know once in the shine, don't vex when you get married. Me nah make trouble stress my brain. Cut checks me, I cut to the chase. Star never second hand, never second in command, never stopping for a second, talking up on the line. Look a jump and sound, I go try and make statements. Don't test
almost ready to get started, so if you can just get your seats. I'd like to introduce now our enigmatic application security manager, Louis Jackman here, who I've had the pleasure of working with for a couple of years. He's going to do a talk, and you can't see it. This is like a camouflaged talk on Kotlin's coroutines in the world of JVM's virtual threads. So if you're familiar with Project Loom at all, you'll understand what the references are here. And whenever I talk to Louis, I'll go up to him and ask him a random application security question. Why is this socket not open on this port? And we'll go deep down, low level, as Louis is an expert in this area, and I'll be bedazzled by various techno babble that I didn't even know that I didn't even know. Even that's what it is. But I'll pass it over now. And do you need this mic? Yeah, I guess so. Okay, so Louis Jackman, everyone.
Thank you. Now, I know what you're all thinking. You're thinking, we know he's an ex-software engineer because of his font color choice on the main slide. But just in my defense, that actually came from the slides being combined together, so I am off the hook for that. From here on, it will all be very readable. So yeah, I'm Louis Jackman. I've been working at Zopa for about 4 years now. Before I jump into my thing though, I just want to quickly give a very brief introduction about what this talk is actually about. So the title, which I have to tell you because you can't read it, is Kotlin's coroutines in the world of JVM's virtual threads. Now, so to provide some background context to this, Java has released Project Loom. This has been a long-running sequence of JEPs, Java enhancement proposals, that have been going on literally for years. I remember hearing about fibers probably 4 years ago or something. So this has been a long-running thing. And while that's been going on, thank you very much, Kotlin coroutines came out quite a long time ago, back in 2018, and they've been getting matured and getting really good library support and just getting really well documented. And again, that layer of polish you get on a really nice feature, and it's been out for a few years and championed by a company like JetBrains that really focuses on developer experience. So I'm Louis Jackman. I'm an application security manager at Zopa, which probably means I'm unqualified to talk about this topic, but you're all a captive audience now, so I don't really mind. But joking aside, I have done lots of work on the JVM in the past. I did quite a lot of Java development in a previous company. It was one of the big, hairy monoliths that was using Play Framework 1. Does anyone remember that? It's kind of grim. And I'm also, in my work in AppSec, I'm also fairly interested in programming language theory and also LangSec, which is kind of feeds into this quite a bit. So I just want to lay my cards on the table here. This presentation is not going to be really good, in the trenches stories about how I used coroutines to battle massive performance problems at Zopa. It is going to be a bit more dry and abstract. But the great thing is that this company has got so many really talented Kotlin developers and Java developers too. So if you do want a more real world discussion about the technology and war stories, speak to one of our native developers. If you're a Kotlin developer here who isn't part of our company, I do have to request that you swan around later and look a bit poachable so that one of our recruiters can pick you out later on. We are hiring. So yeah, thank you. We are Britain's emerging, we're Britain's best bank. That's now our catch line. We are basically our new products being rolled out now in the banking space. We have a pass and peer-to-peer, and like a lot of fintech companies, we lent heavily on the JVM stack. We put Kafka in the mix, and then you've got a stew brewing, right? So before we can dive into a comparison of the two features, we have to start by asking ourselves, what are the elevator pitches? I also didn't pick that font color either, top left. So before we compare them, what were the elevator pitches of the companies that initially released them? How did they sell it? I'm going to do that thing you should never do in a presentation, which is reading straight off a slide. But Kotlin's elevator pitch, when it came out in 2018, so it is quite an old feature now, quite mature, asynchronous or non-blocking programming is an important part of the development landscape. Kotlin solves this problem in a flexible way by providing coroutine support at the language level and delegating most of the functionality to libraries. And you can follow the link there. I should have gone in the Wayback Machine to see if it said this back in 2018, but I didn't. So to give you an ultra simplified view, this is kind of what it looks like syntactically. I'm not going to dig deep into the code because we're doing an overview here, but you can see that it's spinning off a coroutine scope, which is there we go. And then inside here, it's kind of spawning a concurrent task and then doing something else in the meantime. This gets delayed and runs afterwards, and then the whole thing is a scope, and therefore, by the time we leave this block here, we know that all of the things inside have run. And that's structured concurrency, but we'll get to that in a bit. Before we dig into it, though, let's look at the new thing that's entered the space. So an experimental preview of virtual threads came out in Java 19, released in 2022. So this is a pretty new feature. A non-experimental version will appear in version 21, which is to be released later this year. In previous documentations, you'll see them referred to as fibers or lightweight threads, but now virtual threads are the name of the feature. So again, doing the thing you shouldn't do in presentations. Introduce virtual threads to the Java platform. Virtual threads are a lightweight thread that dramatically reduce the effort of writing, maintaining, and observing high throughput concurrent applications. Virtual threads are simply threads that are cheap to create and almost infinitely plentiful. Hardware utilization is close to optimal, allowing a high level of concurrency and, as a result, high throughput. And that's in the JET 425. And this is kind of what it looks like. It's not exactly the same as the previous one, but it's a similar kind of look. You've got a language feature. This is try with resources in Java. And we can see here that you're submitting 2 tasks. They get run in different threads, and then the whole thing shouldn't keep on running after those have run. I don't want to get down into the sticks of code because I want to do that later on. I'm just giving you a light of what it feels like when you read the code. So what is the common ground? Because we can't actually look at these 2 features or compare them if we don't know what their core fundamentals are. What are they giving us? The answer is that they both provide units of concurrency. So at a fundamental level, they are about concurrency, and they're often used, but not exclusively, to dodge expensive system calls, which can block on platform threads. And that's expensive for reasons that I'm going to come to later. But again, to clarify, we have to first ask ourselves, what is concurrency anyway? Before we go into that, concurrency is not parallelism. It's important not to conflate the two. So parallelism is when you do literally multiple things physically at the same time. So that can be done via multi-core processors, SIMD, hyperthreads. Even scaling up a Kubernetes pod is technically a form of parallelism, right? So parallelism is a fascinating topic. Do read the book Java Concurrency in Practice, even if you're a Kotlin developer, because it's an extremely good book on this topic, even for anyone working on the JVM. And also see Rob Pike's talk about concurrency versus parallelism. If you just search for Rob Pike concurrency, it should come up. So from now on, we are in concurrency land. So concurrency, if parallelism is doing multiple things literally at the same time, isn't that what concurrency is? No, concurrency is actually the complete opposite. It's about providing the illusion of doing multiple things at the same time in a finite set of resources. Now, platform threads, which are the threads we're all familiar with in Java, they also achieve this, but they also provide parallelism. And that's why threads are a bit weird, because they do both concurrency and parallelism. Whereas the 2 features we're talking about today only do concurrency. Although you can run them on top of native threads to also run parallelism underneath as well. So I did say this talk was going to get a bit too abstract. It's all downhill from here, sorry. So I want to talk about concurrency. Unix is the predecessor to Linux, OS, Android. You all run Unix systems, right? And it's being up Kubernetes pods, whatever you want. And it's in the 70s. And I think in this room full of such fresh-faced people, no one here is going to be able to correct me on the date. So that's good. And one of the first versions of Unix, at least the portable version in C, was written on the PDP-11. Now, the PDP-11 had an issue, which is at the time, most of the computers you had operators going through them and submitting batch jobs one by one. And that's just inefficient. Operators would be waiting around for other batch jobs to finish. And here's the key thing, the PDP-11, like many computers at the time, only had a single processor. So the machine literally can only do one thing at a time. And then if any of the batch jobs ever slept or screwed up, nothing else can use the CPU in that time. If you think about it, that's a bit of a strange thing, because even on a modern computer, you've got like a quad-core processor, right? But you may have thousands of threads running on it, but literally the machine can only do 4 things at the same time. So that kind of is where concurrency fits in, right? It's about providing the illusion of multiple things progressing at once, when actually only 4 things are literally progressing at once. So PDP-11, there's only one main CPU. How is that possible? The trick is to add a layer of abstraction. And the abstraction layer takes a notion of a task, and it runs them. And it can only run one at a time. It's a poor PDP-11, but it rapidly switches between tasks to provide the illusion that they're all progressing at the same time. Each task also can't dominate all the compute resources, because if you oscillate quickly enough, no one's dominating tasks and stop other people from progressing their tasks. This opens up the ability to have multiple discrete tasks being run at the same time, even though you can physically only do one thing at the same time. Now, for a room full of web developers writing Kotlin, does this problem and solution sound awfully familiar to you? It should do, right? It's very similar to like juggling multiple requests on a web server, when you've only got like a single Kubernetes pod that's only got 2 cores, but you're juggling 10,000 requests. But if you fast forward a bit from the 70s back to the 90s, there's a really exciting new language that's just been released by Sun Microsystems. It's called Java. It comes out with fantastic marketing. It's syntactically accessible. It looks like C, but it is semantically very different. Guy Steele once made a joke about dragging C programmers to Lisp by releasing Java. It has many features like garbage collection and runtime, reflection of runtime, but one key feature I'm going to focus on for this talk is platform threads. So threads were popularized in the 90s in Windows NT and OS2 and other systems. And the key thing here is that they are lighter than forking a whole process. They still provide both parallelism and concurrency. Now, the trick here as well is that if you have multiple cores, which are starting to become a viable thing in that time, not only can the threads be multiplexed onto a single core, but they can also spread out across multiple cores. So you get parallelism and concurrency. Java is also notable because it formalized the memory model in version 5. Not many people know this, but Java is probably one of the first languages that had a fully standardized memory model in the face of concurrency. C and C++ got those in like 2011. Of course, they've always supported it because hotspot's written in C++, but they required non-standard constructs. So actually, Java's quite a big deal in terms of history and the way it popularized standardized threads in terms of how they run. This is what it looked like. So this is just, you just pass it basically a piece of code and it runs it in the threads. I'm massively oversimplifying that, but that's the deal. This, of course, is going to be old Java using a SAM type, and here we're using an anonymous in a class, but these days you'd use a Lambda instead. But this is how it looks back then. So, okay, I guess I can end the talk now because we have a construct that can do parallelism and it can do concurrency. So we just spin off a thread per request, job done. So I can go home. I mean, it knows how to park the threads when you hit a blocking system call. It knows how to transparently multiplex between things. And common web frameworks like K2 and Spring already provide the thread per request model. So problem solved, right? No. The reason it didn't work, and this is what we did for a long time, and to be fair, we still do it today. And actually, you know what? If you're solving a simple problem, seriously, just use the thread per request. It's going to be much simpler. Jetty is fine if you're doing small scale stuff. Don't massively overcomplicate it with incredibly complex async frameworks if a thread per request works for you. But there are some companies where actually it doesn't work. So I think it was probably was it the late noughties where this problem of C10K got really big. It's this idea that people were observing that you couldn't really run beyond, you couldn't really get up to 10,000 concurrent requests on a single piece of hardware, even if it's pretty big iron. So in the 2010s, this led to the popularization of things like Nginx, Node.js, and Go, because they were able to crack this problem. But that's kind of weird, right? Because if we're in this room, we're JVM fanboys. So we know that JVM has got an incredibly good garbage collector. We know the JIT compiler is amazing. So how is it being dominated by JavaScript? This is kind of weird, right? And the reason isn't because the JVM was lacking performance. It was because all of the libraries and systems are based on the concept of using a thread as the unit of concurrency. Now, I could do a whole other presentation on why threads can't they can't switch that quickly and they're quite slow, but that would be a whole other talk, so I can't go into that. You just have to take my word for it that threads are quite heavy, although they have got better throughout the 2010s. The Linux kernels optimize them a lot, but they're still nowhere near as good as an event-driven system like Nginx. So we have this construct, but it's too slow, but we know it solves the problems we have. What do we do next? Now, before I go on to the rest of the presentation, I'm going to be using a term an awful lot in the next coming slides, the term being yield. I'm going to be talking about yielding points and yielding. And that means I have to kind of dump all this stuff on you before I jump into the meat of the two features. So to understand what yielding is in this context, we have to talk about cooperative versus preemptive concurrency. If anyone here is old enough to have used the classic Mac OS system pre-OS 10, you will know that that was cooperatively scheduled, because if a single app didn't cooperate properly, it could stall the entire desktop. And you had the same thing on Windows 3 at the time. So cooperative concurrency is when the task itself gets to decide when it yields. So you can keep running, keep running, keep running. And then it says, I'm yielding now. And it announces that back to the scheduler. And then the scheduler then says, cool, I can move on and allocate to the next person. Unix doesn't work like this. This is why on Unix, even in the 70s, you could fork a process and it could do a while true loop in C, and you could still do other things at the same time because it was actually preemptive. So where do they fit on the hierarchy? JVM virtual threads and coroutines are both cooperative because they require explicit yield points. Unlike a thread, the scheduler can't just say, hold up, you've been running too long, I'm going to run someone else now. Neither of these features can do that, but they are still a bit different because virtual threads, although you still have to do yield points in them, the underlying frameworks can do it for you, and your methods that run on virtual threads don't have to know anything about it. So your methods don't have to be declared with async or suspend, for example. They can just be suspended without the thread knowing about it, without the method knowing about it. Coroutines are totally cooperative. In other words, they have a yield point as well, but they have to be delineated in the code. That's why you have to suspend on the methods, right? But they are still more implicit than async await because you don't have to put await everywhere in your code. And then you have things like promises and futures, which are completely cooperative because not only do they need explicit yield points, but they need to put them at every layer in the call stack. That's why you end up putting await everywhere in JavaScript or Python. None of these things are bad, by the way. It's all a trade-off. If, for example, you go more implicit, there are more concurrency bugs that can happen because you're not explicitly sequencing your code. But then it also makes it harder, more clumsy. You need to write more keywords everywhere and things I'll get to. So I just want to make it clear that everyone knows what I mean by yielding. It's when you're yielding control back to the underlying scheduler. So going back to the previous problem, we've worked out in the early 2010s, threads are a bit too expensive. They cost too much. They take too much memory. We juggle like, I don't know, like 7,000 requests went out of memory because each one's using like 8 megs of stack. That actually isn't true anymore, but back then it wasn't as efficient. So here's the solution. Rather than running on threads, what you do is you poll non-blocking events using something like select or epoll, and then you dispatch to resumed code that was being like paused and then thrown back up. That sounds really abstract, so let me put that in concrete terms. Rather than saying after the HTTP request, do this, you say invoke the HTTP request and trigger this block of paused, unrun code that gets run afterwards. So in classical Node.js, this would be just a callback function. In something like modern Java, it'd be a completable feature, or completion stage. So you have all these abstractions, right? But fundamentally, it's taking a snapshot shot of code, describing it, but not running it. It's just describing how it runs. And then the idea is that eventually, when the operating system polling on the system call says the IO is ready to go, the scheduler has this piece of code you've passed back down to it that it knows to run at that point. So then it triggers. And there are various monadic abstractions over this because completable future is kind of a monadic abstraction, although it doesn't follow the strict laws, but it is quite similar. And the key thing to understand here is that although people do often talk about the massive game-changing nature of async await or do notation Haskell or something else, these ultimately are all just wrappers over the same fundamental concepts, which is something I'm going to come back to. And as you can see, this is kind of an example of a random snippet of code. The actual details don't really matter. I'm just trying to really belabor the point that each sequencing has to be done explicitly via methods rather than just having semicolons splitting your statements. So you kind of have to use like a meta language written in the real language you use. Kotlin does this better though. Even back in the olden days before coroutines, they would still had a better way of doing this because they just had more syntactical sugar in the language. So even when you were wrapping code up in like paused futures and things, it was often much cleaner to read than the Java equivalents. So even pre-coroutines, Kotlin had a pretty good solution to this. So this works, right? This works absolutely fine. You've now got the performance of event-driven systems. You can now do concurrency. And of course, you can back all of this with threads, unless you're using Node.js, I think. But in Java land, we can back up the thread pool, right? So we can also light all the cores in our Kubernetes pod. But like threads, this actually has problems. So API bifurcation is one of them. There's an article called Which Color is Your Function? I'm not sure if anyone's read that. But basically, you end up having to duplicate the whole world into blocking versus non-blocking APIs, and all the type signatures are incompatible. And then if you like have one feature that doesn't have the async equivalent, you then have to start spinning off thread pools and other horror stories, which you don't want to go down. To fix this, some companies have to rewrite everything from scratch. So when Webflux came out for Spring, it seemed to me like they had to rewrite a significant chunk of the stack to make all that work. And that doesn't, in a threaded model, you wouldn't have to do that, right? They could just add more threads behind the scenes and the method would be none the wiser. It also adds cognitive load on developers. So there are non-domain concerns. So we saw the previous talk today about how you want your code to reflect the domain problem you're solving. This is kind of the antithesis of that, because in this model, you've got all these concerns like composing together promises, which have got nothing to do with the domain you're trying to solve, right? And even if you add syntactical support, like async await, you still have these problems. It's a lot cleaner. It is definitely an improvement, but you still have the fundamental issues. So Kotlin in 2018, they saw this problem. They saw developers were struggling with it. So they introduced coroutines. Coroutines look a bit different. So you'll notice first you have the suspend keyword. And this is because you have to announce every layer. Every method that's going through a coroutine has to basically announce it via this keyword. But you'll notice something nice. When we do things which presumably are invoking coroutines, we don't have to do an explicit yield or an explicit await. And this is a really nice feature of Kotlin's coroutines that you don't see in coroutine implementations in other languages. It will, even though it statically knows when it yields, it knows how to syntactically infer it for you, which makes your code read so much more nicely. If you're using something like IntelliJ, though, it will tell you in the margin that you've got a yield point, but you don't have to write it in the code. So this is like actually a really good improvement over async await. So they have to be explicitly marked, no async await, strong tooling support, but it still shares some flaws in the previous slide. You still have bifurcated APIs and you still have some other issues. And it's worth noting that quite apropos of the previous talk about multi-platform support, it doesn't actually exist at runtime. I mean, it exists as a Java object on the heap, but the Java runtime has no concept of a coroutine. It's just a Java object. But that's good because it means Kotlin can then compile the feature away, which means it can then also be implemented on top of Kotlin native. So this actually has benefits. And it's just very safe, stable, and mature. It's been documented for a long time. And in tech, I don't think we sometimes give enough credit to things that are just stable and mature and aren't changing all the time underneath us. And the structured concurrency support is very good as well. Now, so we've had coroutines out for a long while. And then virtual threads have now entered the chat, as kids on the internet would say. And they came out about quite a bit longer, many years later. I'm saying many years later because I've just forgotten off the top of my head, but it's many years later. And they are different. If you want to be kind of technical about it, they are asymmetric, limited continuation, static no yield points, blah, blah, blah. In plain English, what that means is methods don't need to know about them. So in the same way that a platform thread can invoke a method and method has no understanding that it's being spun off in a virtual thread, same in a platform thread, it's the same thing with virtual threads. So methods don't know that they're having a virtual thread passing through them at all. This is really important for reasons that are going to become apparent. Because that means, for example, that if you update the JVM, so your underlying blocking IO system calls know to yield a virtual thread, and then if your web framework knows to spin off virtual threads on the dispatcher, theoretically, you don't have to change any of the code in between, i.e. your application code. Now, in practice, it doesn't quite work that easily, but in practice, the amount of code you have to change is orders of magnitude less than you would if you're migrating from a blocking solution to a coroutine or an async await-based solution. And then you're hoping that all the library authors have added support, which you totally depend on. So yeah, you still have to port frameworks to support virtual threads. They're not magic, but there's a far smaller amount of things that have to be ported for it to work. It's also an inherent construct in the runtime. The runtime, your profiling tools, it inherently knows what a virtual thread is. So even though coroutines probably have better tooling support due to maturity, I think that virtual threads will quickly outpace them just because the JVM, the JVM knows what it is, right? It knows what it is like a normal thread. It can't be compiled away. So that means Clojure and Scala can use them, but if you're targeting stuff like Kotlin native, you can't use them. So if you're doing a project like the previous talk, you're doing a really cool SVG modeling app, you're kind of stuck there because you can't compile away virtual threads because they're a runtime feature. And it is a new technology with less tooling support. And again, we should really focus on that. Like, we should always choose mature solutions that we know aren't going to disappear in 2 years or get broken. This doesn't quite meet that requirement yet, although JVM is quite stable. So when they stabilize stuff, it generally stays stable. So this is a bit of a trick slide because I was going to show you what platform threads look like, but I've just copied the Micronaut example from the homepage, and it's exactly the same code. So I think in Micronaut 4, they claim to support virtual threads. I haven't actually run this code, I'll be honest, a demo sim, but from their documentation, from what they say, as long as you set the build config up right and you run a modern enough JVM, you can literally write standard Micronaut code, and as a Micronaut 4, it can transparently use virtual threads behind the scenes and make it all non-blocking. No suspend keyword required on the methods, and this is really, really good stuff. So this slide is actually a bit too text heavy. But okay, we've got these two features, coroutines and threads. They both fundamentally solve the problem of wanting to have performance of event-driven systems, but also having some of the more convenience of just using threads. And they do that via various trade-offs. So let's go through them. Just to reiterate, coroutines are more mature and virtual threads are less mature. And that's just, inherent in the tech. The documentation is going to be less polished. You can have few examples on Stack Overflow. ChatGPT may even be less helpful at telling you how to fix your code, which is really bad because I rely on that for my job. Coroutines work everywhere Kotlin does. So if you have Kotlin native or Kotlin JS, use coroutines because they're going to work everywhere you go. They're more portable because they're compiled away features. Virtual threads, on the other hand, are inherent to the JVM platform. So they have the loss of not working on Kotlin native, but if you're interested in other JVM-based languages, they just work. I think, for example, Clojure can use them despite them not adding any support for it in the language, just because you can invoke it as a normal Java method. Coroutines do fix a lot of the problems of like using promises and async awaits, but they still do have the API bifurcation problem, where you have to then rewrite your entire framework to make everything suspendable methods. For example, with a virtual thread, theoretically, you could use the Java 8 streaming API to do parallel processing, and actually it's okay if it's backed by a thread pool that uses virtual threads. Then you magically get a parallel job that also handles non-blocking fine, and that just works theoretically. Whereas you have to then introduce Java streams, but then you have to introduce a whole new Flow API to then kind of add support for that for Kotlin. But there is a catch here, which is because you don't have explicit yield points in virtual threads, bugs can come through that otherwise would be more obvious. So if, for example, you're mutating global state partially, or you have data tears where you modify a class on a few fields and then another one intercepts your thread and then modifies the other half, stuff like that is much harder to find in virtual threads because you don't know where the yield points are. So then you have to read concurrency in practice to learn how not to shoot yourself in the foot. Whereas coroutines are quite nice in this regard because your margin in IntelliJ will tell you where the yield points are. And that's only possible because yield points are statically known in coroutines, but they're not statically known in virtual threads, at least like in terms of each method being called. So it's a nice feature, but it does come with a drawback, not knowing the yield points. Virtual threads run through methods that have no knowledge of them, which is something a coroutine can't do. But comes with that drawback I've mentioned. But both of them actually fix quite a few problems we used to have. Both of them, for example, provide concurrency without the performance ramifications of using threads as a unit of concurrency. Using them as a parallelism feature is fine. You should back your app with it. But as a unit of concurrency, platform threads are too heavy, and both of these features fix that problem. They also both avoid explicit yielding in code, which makes code much easier to read. They solve it in a different way, but they both solve this problem. So you don't have a weight or yield all over your code base. And they also both sidestep entirely the need to splice up your code into what's called continuation passing style, which is where you just have callbacks, 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 and it just becomes a bit of a, spaghetti code, or it's massively indented. So even though they have their differences, they both do a really admirable job at solving the problem that's presented to them. They just have different trade-offs in API compatibility, on explicitness of concurrent yielding, of maturity, and of portability on and off the JVM. So the conclusion, as all computing presentations should be, is, I don't know, it depends, which is a bit of a cop-out. But so basically, you've left with no actual answers today. I apologize. But on the plus side, we can now grab some beers. So we have that going for us. Before I dart off and grab my next beer, does anyone have any questions? What version of what, sir? A 21, I think it's experimental. Cool. Yeah. So both coroutines and virtual threads are really, really cheap, much cheaper than threads. Because I think in terms of, I think virtual threads are a little bit more expensive because they have to track the stacks, because they have to obviously pass through multiple methods, which means if they crash, they have to do full stack traces and unwind, which means they're a little bit more expensive. Like the memory consumption is a bit higher than a coroutine, but I think they're both so much better than the alternatives. They're fine. I mean, even in Project Loom spec, they've said, don't even bother doing virtual thread pools. Don't pull them. Just spin off a whole new virtual thread every request, because we are that confident that they're cheap enough. So it's similar to like Erlang or Go. You just spin them up all the time. So I would say to answer your question, cheap enough. Yes, so reactive programming ultimately fits into the explicit yielding style, where because you can't yield through method boundaries without the method knowing about it, you then can't just use a Java streaming API. So then you have to release something like RxJava or Project Reactor, which is one I've used in the past. And then you have to like re-implement all of the constructs you already were familiar with in your base language to match the asynchronous style. And if any of you have used other languages like JavaScript or Python, it becomes this thing where you end up doubling up all the language features, because then you have to know for and then also async for. And then with RxJava and stuff like that, it's kind of the same thing. You already have an API and streaming API that knows how to do kind of Haskell style lazy sequencing and transformation, mapping and filtering, but then you have to re-implement it again on this other platform. I also found when I did Project Reactor many years ago, because the JVM had no understanding of what an RxJava object was, you didn't get like nice stack traces when it crashed, like you would with a virtual thread or a platform thread. Instead, because your code is getting snapshotted effectively and passed down and then triggered again later on, it loses all the stack trace. So then you end up with the classic, oh, this Lambda failed and it got ran on this fork join pool. But yeah, sorry, we don't know anything more than that. So yeah, but they were a very good solution for the problems at the time, because they came out like a decade before, I think, virtual threads and stuff. So they were designed to solve a very good problem. I do think that if you want that model, Kotlin's coroutines flow library is probably the best one, because of coroutines' wonderful syntactical features. I'll pick off one from that side and come back from the middle. Yes, absolutely. You can build coroutines on virtual threads, but you can't build virtual threads on top of coroutines. I strongly suspect that once virtual threads come out, we're going to see a whole range of libraries coming out that basically let you take existing battle-tested coroutine code and then just transparently map it to virtual threads behind the scenes, because you can implement, basically, to give the CS answer, asymmetric coroutines are more powerful than symmetric coroutines, and Kotlin ones are symmetric, whereas virtual threads are asymmetric. And you can implement symmetric in terms of asymmetric ones, but not vice versa, which I know is a bit of a over-the-top answer. That I'll go back to the middle. I don't know if they'll make them faster in terms of speeding them up, but what you could do, for example, is you may discover when you're debugging blocked code base that, oh, it's because we've accidentally backed our code, the thread pool backing our coroutines scope. Unfortunately, someone accidentally ran blocking IO on it. Now, if your web framework is start spinning up virtual threads instead, and if your Java is updated to yield, then theoretically you just will get away with it at that point, because when the coroutine blocks, it doesn't actually block, it just parks the virtual thread. And the virtual thread pool won't pull the threads. So I don't think it will improve the performance per se, but I think it will reduce a massive number of foot guns, which you would otherwise have using coroutines directly on top of native threads. Adrian. Yes, please.
It's just to bring together a couple of the questions. So with JDK 21, when they're introducing Project Loom, they're also refactoring the Java NIO package to use virtual threads under the hood. So where at the moment you might be quite used to using like with context dispatches.io, when you know you're using a library that's doing some kind of blocking IO and then parking that platform thread, for free, you're going to start getting a virtual thread with that. So actually you're not going to need to do that anymore. Probably still recommend to make sure that you don't just ignore it for the sake of it and still do it where necessary. But yeah, you're not going to get caught up as much as before, so you can rely on virtual threads more.
Adrian is the go-to guy at a company. If you want a really good technical clarification, that's quite important. He's our go-to tech troubleshooter. So, go ahead. Yes, that's actually a really good point. If you write code that relies on virtual threads, I don't think it's going to even compile because the methods that trigger it, like the virtual thread methods, just aren't going to exist on the platform, or they're going to fail at runtime when they go through a dynamic proxy or something. So, yeah, I think that's going to be a footcon for many people. Mm. So, yeah, it's a difficult question. I personally would say that the model of not explicitly yielding is used by Erlang and Go, and I think both those languages have more than proven their worth in concurrency. But at the same time, some of the biggest concurrent systems in the world are written in Java, right, which doesn't have this until now. It's honestly, it's a bit of almost a philosophical debate, which is best. I don't know. I think the fully preemptive model, I think it probably makes more sense because ultimately the fully preemptive model reduces cognitive overhead on the developer in the same way that garbage collection reduces cognitive overhead, because then you don't have to delineate between synchronous and asynchronous methods. But as always, as with garbage collection, sometimes if you provide an abstraction, you suffer from Joel Spolsky's leaky abstraction law, which is that actually sometimes it shoots you in the foot. So then some developers can't use a garbage collector because in a domain where actually the abstraction causes more problems than it's worth. And I definitely think there's some domains where that's true for virtual threads. I don't think, for example, something like Rust should ever implement virtual threads because in that domain of low-level system control, you do actually want explicit yield points everywhere. But maybe in a high-level application language, it could be seen as a good trade-off because it lets developers focus on the domain more. But I don't think either technique is going to wipe out the other one. I think they both be alongside each other for a long while. I mean, I'm going to oversimplify here, but it's basically the same. They're using ePOL on Linux. They're using the Windows completion IO ports behind the scenes. They're all using, ultimately behind the scenes, they're using system calls that don't just halt the task and give it a result when it's done. They say, keep polling me and I will tell you when it's ready and give you that thing. So I think it's lib events they use in Node. I'd have to double check. And then there are other ones like Tokyo and Rust, and then virtual threads on Java. Presumably they've implemented something similar. So it is going to be an event loop behind the scenes. It has to be because that's how non-blocking system calls generally are accessed in most system libraries. But the point is, it's about whether you leak that detail up to the user. And it could be argued that the preemptive model of virtual threads or also Go and Erlang leak fewer implementation details of the event loop to the developer than systems that expect a sort of explicit yielding style where you pass down fragments of code for it to run on your behalf. But of course, all abstractions come with a cost. So is that it? I sense you, oh, sorry, one question. No? Oh, well, in that case, I'm not going to keep you from the beer any longer. So thank you for coming to the talk.